Welcome back, my mathematically minded minions and minionettes. Well, as we continue on with quadratics, now that we've reached the halfway point, it's time to start talking about the application of quadratics. So we're going to start to get into some real life situations that are described by quadratics. So what we're talking about today is what goes up must come down. So hopefully as you start to do that, you start to conjure images up about objects being sent up in the air and then coming back to the ground. So we know that as things do that, there is this force, this mystical force that acts upon these things that pushes them so that when you toss something up, it doesn't go up forever, that it is going to come back down. And we talk about that being gravity. So today our equations are all going to focus on gravity and kind of be moving forward from there. So as we look at that, first of all, we know that a function, we've been accustomed to f of x equals ax squared plus bx plus c being our functions that we turn around and we deal with it. And our a right here, this tells us whether it's going to open up if it's positive or whether it goes down if it's negative. It tells us how wide our graph is. You know, this right here, this c value, this constant, this is our y-intercept, okay? This is our y-intercept. So it tells us where it crosses the y-axis. We're used to that. Well, for our functions, as we look at them, there's a couple of things that we need to know. First of all, gravity. We need to talk about gravity for just a second. Now, gravity is this force that acts upon an object. It presses down. And gravity is different for every planet. And for us, gravity is 32 feet per second squared, okay? 32 feet per second squared, or 9.8 meters per second squared. Now, it's important that we know the difference between 32 feet per second squared and 9.8 meters per second squared, because feet and meters are obviously two completely different things. A ruler and a yardstick are much different. So when we look at those, now gravity pushes against us, and it pushes against us as an object goes up, and as an object starts to come back down, it's pushing us down. So it kind of speeds us up. It slows us down as we're going up. We reach that one magical point up there that we call the maximum value, the vertex, where everything stops. Where gravity, we're no longer moving up, we're not moving down. We suddenly pause for that millisecond, that microsecond where everything is fine, and then gravity starts pushing us, making it going faster as we go down. So for our functions, when we look at these, our gravity is going to be listed under the a. The a of our function is going to let us know about gravity. Now, because an object is going up and coming back down, we know that our a will always be negative. It's going to be negative when we look at gravity because the model of ours, when we send it up, it's coming back down. Now, the second part is because we factor in that gravity is working against us in the first half and with us in the second half, our function, how we can tell in our gravity equations, we're going to deal with in feet, it's going to be negative 16 will be our A. If we're dealing with meters, it will be negative 4.9. So notice it's half of the force of gravity looking upon it. Now, so that's all of our A. That's where gravity represents. So we can look at that A and see if it's negative 16, we know we're dealing with feet. We know we're dealing with gravity. If it's a negative 4.9 equation, then we know that we're dealing with the metric system. We know we're dealing with meters. And here again, we're dealing with gravity. Now, our x for us, when we're dealing with these functions, most of the time we're going to be dealing with functions of time. So we probably won't have an x as our variable. Our variable is probably going to be t. So when we start to look at it, it will probably be h of t. And this simply means that we're dealing with a function. We're dealing with height as a function of time. Okay, that means our y value is the height an object goes, and then our x value is t time. So pay attention to what our function is written, because that tells you what information we're going. Now, this thing here in the middle, our b, when we're dealing with these application problems, the b is our initial velocity. It's our initial velocity. It's that initial force, the force that we start off with, that we initially take off. Now we know gravity is going to going to act upon that, and we're not going to have as much velocity once we've gone up a couple of seconds in the air because gravity's pushing us down. It's slowing us down. So it's the initial velocity, and you'll talk about this more in physical science class and how to derive the initial velocity, and we'll look at that a little bit later. But for right now, our B is our initial velocity, the initial force we have. And our C is our starting height, okay? It's our starting height. So when we look at our function, yes, it's a y-intercept in our graph, but that's because when we look at our graphs, if this is time, obviously we can't have any more, we can't go any further back at a time of 0, and this is height over here. When we look at it, if we've got a function and we've got this thing that goes up and looks like this right here, well, this y-intercept right here has to be where we started this because we can't go back. That means at time of 0, our object was this high off of the ground. And from there, then it goes up, it comes back down. This time, whatever this point right here, whatever this 0 is, whatever this root is, should tell us how much time has passed while the object was in the air. So this tells us our hang time. Okay, that's our hang time. That's how much time was in the air. So here's a little bit of application. So let's look at some problems. Let's kind of deal with some stuff, and let's see what happens as we deal with some of these. So we got a cheetah pouncing on an antelope, leaps with an initial velocity of 19 feet per second from a tree branch that is 6 feet off of the ground. How long is the cheetah in the air, and how high did the cheetah leap? Well, obviously we don't have a function here, so we need to write this thing as a function of, so we're dealing with height and time. Now, notice as we look at this, feet, because we're dealing with feet here, because this is an object shooting up in the air and coming back down, we have to deal with gravity. We have to look at feet first because that tells us we're going to be dealing with negative 16 t squared. So there's our first start. Now, we know that our B term, the term here in the middle, should be our initial velocity. So let's look at it. The initial velocity of 19 feet per second. So that's 19 times t. All right. Now, the last thing, the thing at the end says that it's our initial height. That's our starting height. So we look at it. Where did he jump? He started from a tree branch 6 feet off the ground. So that means plus 6. So there's our function. There is our function that models this situation right there. There's an application. We can put this one in the calculator, put it in the computer. We can find this, we can look at some data, and we will do that tomorrow in class. So make sure you've got this equation down and you know what this thing describes. Make sure you write down this problem. All right, so let's look at another one. When Gerald shoots a free throw, his release point is 6 feet off of the ground. If he shoots the ball with a velocity of 20 feet per second at a basketball hoop that is 10 feet off the ground, what is a model equation for this? Well, let's see. What are we dealing with? Well, we've got feet per second, so we know we're doing time. We've got feet up in the air, so we know this one has to be a function of time. So we're dealing with h of t. Because we're dealing with feet, because we see feet here, it has to start off as negative 16 t squared. Good. So now we need our B, our initial velocity. What's the initial velocity? Well, the velocity of 20 feet per second. So 20 t. Now, it is our initial height. What is our starting height? How high do we start at? Well, we got two numbers here. We got 10 feet and 6 feet. Think about it. Yes, you see, 6 feet, that's the initial height that we have it. This 10 feet, that's just how high the basket is up in the air. So we've got Gerald here, stick figure Gerald. He's got his arms cocked. Here's this ball right here. He's turning around and shooting this. He's getting ready to shoot this free throw. Up here, we got this basket, got this rim. He's shooting this. This ball is going to turn around and come up in the air and go from here. So if we were to sketch our graph, here's what our graph looks like. This is time as our x-axis. X-axis down here is time. Y is our height. What is his initial height right here? Where does he start at? He starts at 6 feet. This over here just simply says it's our basket. That's where our target is. This thing would keep going down there, but we're not concerned with that. All we want to know is when does he hit the basket. So There we go. Good. Hopefully you got that one. You're getting pretty good at these. All right. Kelly holds the school record in the discus throw. If the following equation models her record-breaking throw, what is the initial height of the discus and with what force does she throw it? Oh, man. So switch things up on us. Now they give us the function here. So what are we looking at? What force does she throw? What is her initial height? Ooh, they don't tell us whether we're dealing with feet or whatever. I wonder. So let's look at this. First of all, this negative 16 right here, well, there's gravity. And that negative 16 tells us we are dealing with feet. So that right there tells us that we are dealing in terms of feet. All right, so that's a good thing to know. So the first thing, what is the initial height? Well, make sure you write this down on your page. Where do we find the initial height? Where's the initial height? Well, that's our C term. Remember, the initial height is our C. So in this case, what is our initial height? Well, here's our initial height right there. But we can't just put 6 because this is a real world situation. We got to know. What is this? It's 6 what? 6 what? In this case, it is 6 feet. Show me what you know. Now, the next thing is, with what force does she throw it? Well, force, what are you talking about? Force. Oh, the force. Ah, that's that initial velocity. The initial velocity that she throws this with. And in this case, we know our initial velocity is right here. It's our B term right here. Our initial velocity is our B. So it's 95. But we can't just put 95. 95 what? We got to have it. Ah, it's feet per second. So she throws this discus at 95 feet per second. So, guys, you better watch out. She is hurling this thing quick. We'll have to pull out our graphic calculators and see exactly how high does she throw it and how far does she throw this thing. So, pretty cool. All right, so let's try this one. Stevie tosses a quarter off of a roof that is modeled by the function below. How high was the building that she tossed the quarter from? If it lands on a balcony that is 218 feet above the ground, how long was the quarter in the air? Whoa! She tossed this thing up. The balcony is 218 feet, so she is, I don't know, she is up there. So let's look at this equation. A couple of things. We need to look at the A, the B, and the C. Remember what each of those things tell us. The A, hopefully you know, tells us that we're dealing with gravity in terms of feet. We can see that up in the air. That our B term right here, this B is our initial velocity, and this C over here is our starting height. That's where we start from. So let's answer the questions here. How high was the building? The building was 506 feet tall. There is our initial building. We know it's 506 feet tall. The second part of this thing, we will answer this one in class. So we'll have to pull out our graphing calculators and figure this one out. So good job there. All right, now, the following equation describes an object being launched from a catapult. What information can you derive about this situation? Whoa, totally strange right here. All right, so go ahead and hit pause. See if you can fill out the information, and we'll talk in just a couple of brief moments. All right, so hopefully coming back here, you've looked at this thing, negative 4.9 t squared. Well, this negative 4.9, this 4.9, we know tells us that we are dealing with, the 4.9 tells us we are dealing with one, gravity, okay? But it also tells us that we are dealing in terms of meters. Gravity in terms of meters. That's what this negative 4.9 tells us. Okay, so that 97 is not 97 feet now. It's 97 meters per second. And what is 97 meters per second? That is our initial velocity. So this catapult is launching this thing at 97 feet per second. So, excuse me, 97 meters per second. Oh, feet would be an understatement. This thing's going meters. A meter's looking at over 3 feet per second. So times 97. So this thing is really launching. What does that 5 tell us? That the catapult, that the launch, it launches from a height of 5 meters, not 5 feet, but 5 meters. So over 15 feet up in the air when this thing launches. So this is a big catapult. We're going to have to plug this thing in and figure out how high is this thing launching things and how long is this thing in the air. Maybe we need to figure this out. Well, hopefully this gives you a little insight into some application of these. We will start working these problems in class, and I will see you tomorrow. Have a great evening.